Today we're going to be beginning our conversation about how particles interact in solution. This is actually going to be an ongoing conversation because it's kind of the backbone of chemistry, right? That's really what chemistry is all about. Is how are these particles actually interacting in solutions, in reactions, stuff like that, okay? So let's think about when something dissolves in water, when we make a solution. For example, calcium chloride. What is calcium chloride? What's the chemical formula of calcium chloride? CaCl2. How can you classify that substance?
Ion.
It's an ionic substance, right? Will it dissolve in water? Yes. When something dissolves in something else, we say that to be soluble. Good. In next class, we will talk more about solubility rules and stuff like that, okay? So CaCl2 is soluble in water, and it's ionic. When an ionic compound dissolves in water, what does it do?
Splits into ions.
It breaks up into its ions. What is that called? Dissociation. And that's different from, it doesn't disassociate, it's just dissociate. Okay? So ionic compounds will dissociate in water. So if we were to draw this particulate diagram, what would water look like?
One big and then two small. It's like Mickey Mouse.
Yeah, it looks kind of like Mickey Mouse, right? So we might say water is like this. And then CaCl2, we would need a symbol for calcium and then a different symbol for chloride, right? And we have two chlorines there. So I might draw the calcium like this, like a little circle, and then my two chlorines like that. Those chlorides are actually supposed to be about the same size. I just cannot draw circles the same size. And the chlorides are actually significantly larger, or they're much larger than the calcium ions, because that's what happens with ions. Okay. So when we put this in water, so starting off, so here's my calcium chloride, and then my water molecules. So question here. Are the water molecules going to randomly arrange themselves around the calcium chloride, or are they going to arrange themselves in a certain orientation? This is a loaded question.
Sure.
Because it's not going to be random. There is a specific orientation that the water molecules take around the calcium chloride. So how can we describe water? It's a polar covalent substance. There's a partially positive end and a partially negative end. And so what ends up happening is those water molecules are going to arrange themselves around the calcium chloride in a way that you have negative and positive interacting. Okay? Which part of my water is going to be partially positive? The hydrogens. So the hydrogens are going to orient, the water molecules are going to orient themselves so that the hydrogens are closer to which ion? The chlorides, and then the oxygen in the water will be closer to the calcium. So first off, here's like my solid calcium chloride. I add water to it, and the hydrogens are going to attract to those chlorides. And if that attraction is strong enough, it will pull apart the ions in calcium chloride, dissociating it. So then this would become this. We'd have a chloride ion that's surrounded by water molecules where the hydrogens are closer to it. So something like this. And then we'd have two of those. So we'd have another chloride ion with my water molecules around it. And then we'd have my little calcium ion. How are the water molecules going to arrange around the calcium?
No,
Oxygen towards it. So we get that interaction. But all those ions are surrounded by water molecules. And we have more than just one formula unit of this calcium chloride dissolved in water. We have a lot of it, right? Now, what if that attraction between the water molecules and the ions was not strong enough to pull apart those ionic compounds? What would we call that? Not soluble or insoluble, okay? So some of our insoluble ionic compounds, which again, we'll talk more about solubility next class, those insoluble ionic compounds, those water molecules, that interaction is not strong enough to pull it apart. Questions?
Is there a difference between why calcium is surrounded by 4 but chloride?
No, it was just the way I was drawing it. So the number of water molecules around it really doesn't matter. Because and there's a bunch of other water molecules in this solution as well, we just didn't draw them. All right, so let's talk a little bit about electrolytes. Electrolytes. Actually, before we talk about electrolytes, let's do a review of strong acids and strong bases. So on the side of your paper, like over here, we'll do our review. And if you look on my page here, I actually wrote my review off on the side. These dissociation equations that we'll be writing don't take up a huge amount of space. Acids. Acids. How do we know something is an acid?
There's a reason there's not power. So
If we look at the chemical formula, how do we know something is an acid?
if it's donating a hydrogen,
If we look at the chemical formula, how do we know something is an acid? Starts with hydrogen. For right now, that's all you need to know. If it starts with hydrogen, it's an acid. Okay? So, for acids, strong acids, let's talk about binary first. What does binary mean? Two things, right? What's one of those things? Hydrogen. And the other thing would be a non-metal. So for our binaries, there are only 3 binary strong acids. HI, HBr, and HCl. Any other binary acid is not strong. So like HF, that's a weak acid. And then our ternaries, the rule of thumb is you need to have at least 2 more oxygens than hydrogens for it to be strong. So 2 or more. O's, then H's. Now ternary, remember that was kind of a misnomer because we do have some acids that have more than 3 elements in it. But only those that contain oxygen will be strong, and only those that have 2 or more oxygens and hydrogens you will have, it'll be strong. So for example, HNO2 versus HNO3. How many more oxygens and hydrogens are there in HNO2?
2. No.
1. There's only 1 more oxygen and hydrogen. So HNO2 is a weak acid. And then in HNO3, there are 2 more oxygens and hydrogens. So that is a strong acid. And then any acid that contains carbon is weak, regardless of the number of oxygens compared to hydrogens. If it contains carbon, it's going to be a weak acid. If it is an acid. These are going to be our organic acids, which are all weak.
Why?
We'll talk about that in Unit 7. So a lot of this acid and base stuff, it's just a little bit of a preview for right now. You just need to know what the strong acids and bases are and what the weak and how to figure out which ones are weak. We'll talk about the acid structure and what makes them weak versus strong later. But for right now, you don't need to know any of that. Bases. Bases. There are a lot less rules for bases, but strong bases are, first of all, how do you know if something is a base? In general, most bases contain what? OH, hydroxide. Most bases contain hydroxide. So strong bases are going to be the hydroxide with a group 1 metal strontium or barium. So not all group 2 metals are strong with hydroxide, only strontium and barium. And then any group 1 metal with hydroxide is going to be strong. So like sodium hydroxide, that's a strong base. Lithium hydroxide, strong base. Barium and strontium hydroxide, strong bases. But like calcium hydroxide is a weak base. Aluminum hydroxide is a weak base. Okay? And then one that you need to know for right now is if you ever see NH3, what is the name of that? Ammonia. That is a weak base. So just know, if you ever see that, it's a weak base. All right, so now in talking about electrolytes, a strong electrolyte is something that if you run an electric current through it, it's going to conduct that charge. Like if you put a light bulb in it, it would light that bulb really brightly, okay? Because we have a lot of dissociation occurring for strong electrolytes, so you have a lot of ions being formed in solution for that current to pass. So the strong electrolytes are going to be things like your soluble ionics, your strong acids, and your strong bases. All of those form a lot of ions in solution. They completely dissociate when they are dissolved in water. So they produce a lot of ions for that charge to transfer. Weak electrolytes are going to be ones where only some dissociation occurs. It's only a partial dissociation. So not a lot of ions are being formed in solution, so it can't conduct as much of a charge. It'll still conduct some, but not a lot. So if you imagine that light bulb, it'll only be dimly lit. I feel a joke analogy about students, and yeah, we're not going to go there. All right, so weak electrolytes are going to be your weak acids and weak bases. And also, we're not going to deal with this too much right now, but your insoluble ionics are going to be weak electrolytes because there is still some dissociation that occurs. For right now, though, for this unit, it's either soluble or insoluble. We're going to spend an entire unit later in the year on those insoluble solids and how figuring out actually how much does dissolve, because there is still a little bit. Okay. And then non-electrolytes are going to be things that don't conduct any charge. There's no dissociation whatsoever. There are no ions being formed, which would be like what? Like glucose or sucrose, which would be, those are both polar, but they're both, what types of compounds? Covalents. These are going to be our covalents. Okay. Because the glucose and sucrose will still dissolve in water. There's just no dissociation into ions because there's no, they're not made of ions.
So anything ionic is either strong or weak, and then only covalent is.
Exactly. So we're going to look at each of these, and we're going to identify if they are a strong electrolyte, weak electrolyte, or non-electrolyte. For those that are strong, we're going to write the dissociation equations. All right, so looking at this first one, HClO4. What type of compound is that? It's an acid. What type of acid? Is it strong or weak? Strong acid, because there's 3 more oxygens than hydrogens. So since it's a strong acid, what type of electrolyte? Strong. Strong acid, strong electrolyte. Strong. Strong, weak, weak. So since this is a strong electrolyte, we're going to write the dissociation equation. So HClO4, when it dissociates, what ions does it dissociate into?
H positive plus Cl7.
ClO4 minus.
Okay.
Those are the 2 ions that make it up. Do not confuse dissociation equations with decomposition reactions. different things. This is, imagine you put that in water. What does it break up into? That ClO4 minus is one big unit. That's one polyatomic ion. It cannot break down further without going through a chemical reaction, which would be like a decomposition of some other type of reaction. Okay? All right, C6H12. What type of substance is that?
Non-electrolyte.
Because it is
Covalent.
covalent. That is a covalent substance. It's actually non-polar covalent. So therefore, since it's covalent, it is a non-electrolyte. And we have no dissociation equations right because it is not a strong electrolyte. Next one. LiOH. Strong base, because it's a group 1 metal with hydroxide. So since it's a strong base, that makes it a
Oh, it's a strong electrolyte.
strong electrolyte. So we can write the dissociation equation of that. What does that dissociate into? Li plus OH minus. The lithium ion and the hydroxide ion. All right, NH3. What is NH3? Well, what is the name of that? Ammonia, which I said make sure you recognize that because that is a weak base.
What about ammonia? Is it also
Yes. Weak base, which makes it a weak electrolyte. So technically, this says if it's strong, write the dissociation equations. So technically, you don't have to write this dissociation equation. But let me give you a little bit of preview into what we're going to be doing in a later unit. Write it in green. Right, so when weak acids and weak bases are added to water, they go through a reaction with water. For right now, you don't need to know this, but I would still write it down because, like I said, this is a little preview into a later unit. What's that arrow I just did? Yeah, it's an equilibrium arrow. Okay, we're going to be using that a lot in a few units. So when this reacts with water, the products are NH4+, which is ammonium, and OH-. See how there's still some ions in this reaction, in this dissociation. There's still some ions being formed. It's just not a lot of them. That's why there's still a little bit of an electrolyte. It'll be that dim bulb. Okay? NaCl.
strong base? Wait.
It's a soluble ionic,
I was thinking about NaOH.
which makes it a strong electrolyte. So we can dissociate that into what?
Na plus.
Na plus and Cl minus. All right, the next one, HC2H3O2. What type of substance is that?
It's an acid.
It's an acid. Is it strong or weak? Weak. Why? Got carbon. Got carbon in it. So this is a weak acid. So therefore, what type of electrolyte? Weak electrolyte. And just like with the ammonia example, we can write the dissociation equation, though you are not responsible for this yet. Not for this unit. But a little bit of a preview. Just like with ammonia, we're going to add it to water. Equilibrium arrow. The products of this are going to be the acetate ion and hydronium. Again, still ions are present, just not a lot of them. So it's not a complete dissociation. Can you guys see that okay? I know that green sometimes doesn't show up that well. Here, is that better? All right, and then the last example, NH4Cl. What type of substance is that? That is ionic. This one's tough to, some people have a hard time with this one. This is ionic, and this one is soluble. Next class we'll go over solubility rules, but anything with ammonium is pretty much going to be soluble. So So it's a soluble ionic, so therefore it is strong electrolyte. So when it dissociates, what does it dissociate into?
Ammonia positive. So NH4 plus.
NH4 plus and Cl minus. Please do not take shortcuts on the charges. If you leave off charges, you're changing the substance. Bless you. Okay? There will be several places here in this unit where we will be writing equations where you need to have charges in it somewhere. Don't leave them off because you will get it wrong. Okay? All right. Moving on. Molarity. Molarity. What is the formula for calculating molarity? Moles of what? Moles of solute over liters of solution. And that is molarity. What's the symbol for molarity?
Capital M.
Capital M. All right. So for molarity, actually for all solutions, what we, the determination for what's the solute versus the solvent comes down to amount. The solvent will always be in the greater amount in terms of moles than the solute. That's really all it boils down to. So even if they're almost equal, the one that's in the slightly lower amount is the solute, and the thing that's in the slightly higher amount is the solvent. For most of our aqueous solutions, even the more concentrated ones, the water, remember that's what aqueous means, the water is our solvent, the water is going to be in significantly greater quantity than the solute. When you dissolve, most of you dissolved sodium chloride in water today. Some of you didn't because your procedure did not say to add water. But a lot of you did. You added water to your mixture and your sodium chloride dissolved in that water. The volume didn't change. The amount of sodium chloride you had was so tiny compared to the water. And when water dissolves something, those ionic compounds kind of, the ions take up barely any space and they kind of fit in between the water. So even though this says that you're dissolving it in like 1 liter of water and 500 milliliters of water, those are going to be the volumes of your solution, is what I'm getting at here. Okay? And for this problem, only for this problem, we're going to ignore the sig figs of our volumes and just worry about the sig figs of our solute moles, okay? So take a moment to go through and do these calculations. All right, so now that you've had a chance to do these calculations, I'm not going to go through how to do them all, but you know, let's say 1 liter was 1, this one was 2. Okay. So what'd you get for number 1?
0.875.
Yep, 0.875. What are your units?
Mole. No,
You could do a big M, or you could write it as 0.875 moles per liter. I don't care. Either one. Okay. What about for number 2? 1.75? What about when it's dissolved in 100 milliliters? 8.75. And then in 6 liters? 0.146 moles per liter. Okay, that one was pretty easy because you didn't have to do really any conversions there. It was just dividing. The point of this was to show that when there's more of the solvent, when there's more water, the concentration is lower. It's more dilute. Okay? When it's less water, the concentration is greater. It's more concentrated. So now, numbers 4 and 5. Numbers 4 and 5 are describing how to make solutions. Okay? You need to be able to describe and do all the math necessary for making solutions. All right? this first one, number 4. How would you prepare 500 milliliters of a 0.05 molar solution of copper 2 nitrate? We're going to say this copper 2 nitrate is solid. Ever since the Windows 10 update, the formatting has gone all messed up. Okay, so this is from the solid copper 2 nitrate. So I need to measure out a certain amount of the copper 2 nitrate and then dissolve it into 500 milliliters of water. This is what I do all the time for your labs. Figuring out, like doing stoichiometry and doing the dilution formula is what I do constantly. Okay, when I need to, say I needed to make a 0.05 molar solution of copper 2 nitrate, I would first look at how many milliliters of that solution each lab group needs, and then multiply that by however many lab groups I have across all 3 classes. And then I always round up, and I always add a little bit more because people might pour out too much, make a mistake, we have to do lab makeup, whatever. Oh, pop quiz. What is the device name that we make solutions in? Volumetric flask. Okay, we make solutions in a volumetric flask. Volumetric flasks are very precise for 1 volume. Okay, and the different volumetric flasks are measured to different sizes, or different volumes. We have 4 different size volumetric flasks here. There are more, but we only have 4 here. We have 100 milliliter, 250 milliliter, 500 milliliter, and 1,000 milliliter. Okay, so those are the 4 size volumes I can make. So say I'm doing the math and I figure out that, oh, I need 600 milliliters of this solution for all of my students to use. I'm making 1,000 milliliters because I'm rounding up to the next size flask. Okay? All right, so I need to calculate, doing some stoichiometry, how many grams of copper 2 nitrate I need to measure out. How am I going to do that? What am I going to do first? Find the moles. How am I going to find the moles of copper 2 nitrate? Yeah, so we know the milliliters, we know the concentration. Remember, molarity is moles per liter. If I know the molarity and I know the liters, I can find the moles, because molarity times liters equals moles. Algebra, right? So my molarity is 0.0500. What's my volume in liters? 0.500000, because of, those lovely sig figs that you love. Liters. So this will tell me the number of moles of copper 2 nitrate, and then I can do a quick mole conversion using the molar mass. So how many moles is that? .0250 moles of copper 2 nitrate. And then I'm going to do a mole conversion, converting that to grams. So we need the molar mass of copper 2 nitrate. It depends on what you're starting with. With this, since you're starting with the solid, you have to have grams. That's the only thing we can measure of the solid that can get us to moles. So what's the molar mass of copper 2 nitrate? 187.57. So then when we multiply those, you should get 4.69 grams of copper 2 nitrate. Right, so now the actual steps for what you're going to do to actually make this solution. So you would need to measure out the 4.69 grams of copper 2 nitrate. Now it's really the only thing you can do with solids is find the mass of them. Okay? So we measure out the mass, 4.69 grams of copper 2 nitrate solid, and then we would put that into the appropriately sized volumetric flask. What size volumetric flask do you think we're going to use?
So we have 500 milliliters, so that'd be like 50, maybe 750 milliliters.
We would put it into a 500 milliliter volumetric flask
But
because
you-
that's the exact volume we're making.
Turn it over.
No.
Why did it just hit the brim?
The volumetric flask has a line for exactly 500 milliliters. Well, you're going to use one in your next lab, so yeah. You would put that into a 500 milliliter volumetric flask, which has a line on the neck for exactly 500 milliliters. And then what do we do? So we put the solid in there, and then what do you think we're going to do? Add water. What type of water are we going to use? Distilled water. You're going to fill to that line with distilled water. And then you will put the cap on the volumetric flask and you will invert it a bunch of times to make sure it's thoroughly mixed and that solid is dissolved. And then you transfer it to another container. And there you have a 0.05 molar solution of copper nitrate and you have 500 milliliters of it. Okay? If you used a different size volumetric flask to get the same concentration, you would need to do the math over again to figure out how much of the copper nitrate you would want to measure out. Now typically when, there's a step I skipped, and that's actually once you put the solid in the volumetric flask, you don't want to fill it all the way up at first. You want to fill it up about halfway with distilled water, and then mix it up to make sure that solid gets nice and dissolved. And then you would fill up the rest of the way to that line, cap it, invert it a bunch of times. Okay? All right, so this is when we're coming from a solid. What if we already have a solution? What if we already had a solution that we want to make another solution from that? Okay? This would be a dilution. This is where we're doing a dilution from a more concentrated solution to a less concentrated solution. What is the formula for doing dilutions? M1V1 equals M2V2. All right? Now typically, you want to make your greater concentration your M1. So here, we have a 0.5 molar solution of copper 2 nitrate, but we want a 0.04 molar, and we want 250 milliliters of that 0.04. So we want to calculate how much of that greater concentration do we need to then dilute. Okay? So my M1 in this case would be what? Which one's the greater concentration? The 0.5. V1 is what we're calculating. M2 is what?
Oh, wait, no. 0.4.
And what's my V2?
0.25.
We can actually leave it in milliliters here because it's a ratio. But only for the dilution formula can you do that. When you're doing stoichiometry, you need to convert it to liters. All right, so go ahead and do that math and figure out what V1 is. What did you get? Should have gotten 20. How many 6 figs does your answer have? 2. Because the 250, there wasn't a decimal point candidate. We only want 2 things, but we need 20 milliliters of the more concentrated. So our steps, we would need to measure out 20 milliliters of the 0.5 molar copper 2 nitrate solution. Now, how do you think we're going to measure that out? What device do you think we're going to use to measure 20 milliliters? We can use a graduate cylinder, definitely. Is there something that's more precise? A volumetric pipette is going to be more precise. We haven't used one of those yet. We've used a graduated pipette, which would be more precise than a graduated cylinder. But we have volumetric pipettes, which are going to be your best bet. Okay? So we measure out this with a volumetric pipette. Volumetric pipettes are kind of like volumetric flasks, where they're only certain sizes. You would want to use a 20 milliliter one. If there isn't a 20 milliliter one, you might need to then use it. You would have to go to a less precise device, like a graduated pipette or a graduated cylinder. But if you have, like if that's what you need and you have that size pipette, use it. Okay? You want to make your measurements the most precise as possible. And we would add this to what? What size volumetric flask are we going to use for this one? 250 milliliter volumetric flask, because that is the amount of solution that we are making. And then what do we do? Fill it with distilled water until we reach the line. And then cap and invert a bunch of times to mix. Now, when you make these solutions, and you're adding the water to the volumetric flasks, what happens if you go above the line? The concentration does change. Can't you just take some of the water out? No, because as soon as you're mixing it, those particles are all moving around. You'll be actually taking out some of the moles of your solute as well. So if you go over the line, it's an error. That's something you need to make note of, because it will affect your percent error or your percent yield, depending upon what you're going for in that lab. Okay? So if you go above the line, you can do one of two things. Deal with it, move on, make note of the error, or remake your solution, which that will never be an option for you guys, because I don't want you to waste chemicals. Okay? When you're filling up these volumetric flasks, we have those squirt bottles with distilled water filled up like a lot of the way with with distilled water just from the tap, not the tap, but the jugs. And then when you get close to that neck, then you stop and you squeeze the bottle and slowly fill it. Okay? All right. One more problem and then we're done for today. Determine the molarity of total ions in a solution prepared by dissolving 9.82 grams of copper 2 chloride in enough water to make 600 milliliters of solution. And then, what is the molarity of chloride ions? So we're answering two questions here. What's the molarity of the total ions and the molarity of chloride ions? Well, what do you think we should figure out first?
The moles are 9.82 grams.
Yeah, the 9.82 grams, let's convert that to moles. That's a good way to start. When in doubt, go to moles. So we need the molar mass of copper 2 chloride. $134.45. And how many moles is that? 0.0732, or sorry, 0.0730 moles of copper 2 chloride. Okay, now what?
I find you do moles over liters. So
Okay, how many liters do we have?
0.6.
0.600 liters. And what's that? Like, calculate it. What you get?
You get 0.122.
You get 0.122 moles per liter of what?
CuCl.
That's CuCl2. How many ions does CuCl2 have? Well, let's write out the dissociation equation. When we dissolve CuCl2 in water, what does it dissociate into?
Cu positive. 2 positive.
And
2 Cl negative.
don't forget to balance your dissociation equations. All the ones on the first page that we did, all of them were 1-to-1. We didn't have to worry about balancing, but sometimes you do have to worry about balancing your dissociation equations. So how many total ions does this dissociate into?
0.1. Oh, 2.
3. It dissociates into 1 Cu2 plus ion and 2 Cl minus ions. So that's 3 ions per one of these. Okay? So technically what we're doing here is a stoichiometry problem. We're going to take the 0.122 molar CuCl2. We have 3 ions per 1 CuCl2. So really you're just taking that concentration and multiplying it by however many ions you have. 0.122 times 3 is 0.366 moles per liter of ions. So that answers the first part. What about the chloride ions? Just the chloride ions. How do we do that?
You multiplied it by 2.
What are we multiplying by 2?
The 0.1.
The 0.122. Which is?
0.244.
0.244. And that would be the molarity of the chloride ions. Okay? So that's it for today.